Now we focus on the marriage before conquest algorithm. This is a very interesting algorithm because in some sense it's the opposite of divide and conquer, and that's why it's called marriage before conquest. In general, divide and conquer idea is that if you have a problem and you cut it in two pieces, then each piece can be solved easily. So in other words, we cut it into two halves, and then we recurse over here, and then we recurse on the other half. And once we've done recursing and solving the problem on these two halves, we then merge them. So that's the paradigm of divide and conquer. Divide, conquer, and then merge. In the marriage before conquest, we do this in opposite order. So basically the idea here is that you divide the point set in half, then you merge them without actually computing the upper whole, and then you recurse. So that's why it's called marriage before conquest. So formally speaking, this problem finds a median x coordinate, or if you want, just samples a random point. So like in your implementation, you can just sample a random point and use its x coordinate to divide. Divides the point set in left and right. So there's this left point set and then the right point set. And then it finds the common tangent between the left upper hull and the right upper hull without actually computing the convex hulls or the upper hulls. Once you find this upper tangent, then we know that so this is the pseudocode. Once we find the bridge or the upper tangent, then we know that all the points that are below this bridge cannot be part of the upper hull, right? So they can be deleted. I guess they can be deleted. And now we are essentially can recurse to the left and the right. So now we have a point set that is complete to the left of the bridge, another point set that is complete to the right of the bridge, and then we can repeat. Do this thing, find the bridge over these two halves, prune, and then recurse. So obviously the mysterious part is part number 2, but let's ignore this and let's just assume that we can solve this. Finding the median takes linear time, partitioning into left and right takes linear time, removing the points below the bridge takes linear time, and then the recursion is just a normal recursion. So if step 2 can be done in linear time, then we get the same recursion as the quick sort or merge sort, we get the same recursion as merge sort as well as divide and conquer, so we get in log n. But crucially speaking, in the second project, you can prove that if the step 2 can be done in linear time, then the total running time is n log h. So in fact, this is the ultimate convex hull algorithm that can have a running time between smaller than nh and smaller than n log n. And on top of that, we can show that with respect to the parameter h, this is optimal. In other words, we can show in some algebraic decision tree model, and we're not going to do that here, that in the worst case, given parameters n and h, you cannot do better than this. In other words, there's an input that has a convex hull size h such that its convex hull cannot be computed faster than n times log h. So it means this is optimal. And in the rest of this lecture, we're going to focus on how to find this bridge. If you can't find this bridge, then implementing this algorithm is relatively easy, up to some issues that we're going to talk about those in the exercise classes.